Today we'll continue talking about refraction, and in particular talking about the formation of images, both virtual and real images, due to refraction, and of course an important application is lenses, especially thin lenses, and we try to do some ray tracing with lenses. Okay, so as a brief review, last time we talked about refraction, and the main law that governed the refraction of light was Snell's law, which said if you have a medium with index of refraction n1 and another with index of refraction n2, and if you have light incident, let's say from medium 1 to medium 2, and you have this ray that forms an angle theta 1 with the normal to the interface between the two media, then what happens is depending on whether n2 is larger than n1 or smaller than n1, this light either bends away from the normal or toward the normal. So if n2, for example, is smaller than n1, you bend away from the normal. Something like this happens, theta 2. And the relationship is n1 sine theta 1 is n2 sine theta 2. So if, of course, n2 is larger than n1, you move toward the normal, you bend this way, and can always satisfy this equation. If n2 is smaller, you may not find a solution to this equation. You may find that your sine theta 2 is going to be larger than 1 if you just solve for sine theta 2 in that equation, and then there is no angle. So we have, for n2 smaller than n1, we have total internal reflection when theta 1 is larger than theta critical, such that n1 sine theta critical is n2. And that means theta 2 is 90 degrees. So if you have a larger angle, then you're not going to find the solution. That's when the sine of theta is 1. So that's the critical value of the angle. From this, you can solve theta c to be the inverse sine of n2 over n1. Okay, so that's what we discussed last time. And now let's try to think a little bit about what we see. Like if you have, for example, an object at the bottom of a swimming pool, how different would it look to us, right? So what are the consequences of this bending of light in our visual perception of objects that are, you know, across an interface? Maybe you have your spoon in a glass of water. It kind of looks different, right? So the light bends as it reaches our eyes from the spoon, because it has to go through an interface between the two different media. And so the simplest case is just a flat interface like this, right? So let's say image formation with a flat interface. So what happens? So let's say you have a point object or point source of light. Kind of looks like this. Here, let's say we have n1. Here we have n2. So And let's say N2 is smaller than N1. So let's say here is, for example, like water. As an example here, maybe we have air. Okay, so again, the ray model of light says there's going to be rays emanating from this source, and they move in all possible directions. So one ray here, another here, right? They go in all different directions. Now, so that's a point, right? So what's going to happen? Well, as these rays enter air, this second medium, it has an index of refraction that's smaller than N1. So they're going to somehow bend away from the normal. The normal one just continues, right? But this one bends a little bit away from the normal. And this one also bends a bit more away from the normal. Okay, so if you trace these back, well, for one, I mean, they may not all coincide, especially if these angles are large at one point. So the object may become a bit blurry. But a more important effect is that the object will look closer, right? So there's like a virtual image, right? Again, these rays, the dashed lines are not real rays. There's no light there. The actual light is the incident light. But if you trace back these rays that enter the new medium, it seems they're coming from a point that's closer to our eyes. So if you're looking here, it appears that that object is closer. So that's an effect. You know, if you, I don't know, drop something to the bottom of a swimming pool and you look at it, it could be a very deep swimming pool, but visually it looks like that it's closer than if the pool is empty. Okay, so we can also figure out like how much closer it is, especially if the angles are small. To a good approximation, we're going to get a point image for a point object. So, small angle approximation. And that's when, you know, sine, tangent, and the angle itself are kind of similar. So, again, let's say here we have N1, here we have N2 smaller than N1. The object is a distance s from the interface here. Okay, so where would I see the image, right? So let's consider first the normal ray is perpendicular to the interface, so it just keeps going. Then let me consider another ray. So it forms an angle theta with the normal to the interface. And we're assuming theta is small. Okay. So let's call it theta 1. And then as it's refracted, it forms an angle theta 2 on the other side. Okay, so if I continue this ray and see where it intersects with this normal ray, again, if this angle is theta 2, here I have theta 2. So let's call this distance, call it S prime. So this is object, this is, say, the image of the object. We haven't checked that it's kind of independent of the ray, we're just considering two rays, the idea is what we're going to see is that if theta is small, the position is going to be independent of the angle of which ray we consider, and in that limits we can approximate the image of a point object to be a point. So let's say this distance here to the image is s prime. Okay? So how would I find it? Well, technically, like from here to here, if you want to write exact expressions, let's say that distance is L. L is going to be S tangent theta 1. Right, so here I have theta 1. So L over S is tangent of theta 1. So L is S tangent theta 1. And if you want to write S prime, we have S prime is L divided by tangent theta 2, right? Tangent of theta 2 is going to be L over S prime. So that implies that S prime is L over tangent of theta 2. Okay, so if I eliminate L, I find S prime is S tangent theta 1 over tangent theta 2. That's an exact expression, right? And then the relation between theta 1 and theta 2 is that sine theta 1 over sine theta 2 is n2 over n1, right? That's Snell's law. So if you want to solve these exactly, yeah, there's not going to be S prime, kind of depends on what theta 1 is. But in the limit of a small theta 1, so small angle approximation, sine, let's say, sine theta 1 is approximately equal to tangent theta 1. And if theta 1 is small, then theta 2, again, it's going to be small, right? Sine theta 2 is sine theta 1 times n1 over n2, which is a number that's, you know, order 1 or 2, 3, something like that, or half. Well, we're assuming in this case that n1 is larger than n2, so. But if theta 1 is really small, theta 2 is going to be very small, and then we can approximate sine theta 2 to be also approximately equal to tangent theta 2. So that means that S prime, and let's now not worry about the signs, so I just treat both of them as positive numbers, is length of, is S times n2 over n1. Right, so n2 over n1 is a number that's smaller than 1, and then this distance becomes shorter. So the object is closer, and then in this approximation, you know, see that the result ended up independent of the actual angle. So if you have also a different ray, as long as you are in the small angle approximation, as long as these distances are much longer than these vertical distances, then if you have a different ray going off at some different angle, as long as we are in this approximation, again, it gets refracted in a way that it looks like it's the refracted ray is coming precisely from the same point on this normal line that we found. Okay. All right, so that's a cleaner picture describing what we were talking about. So if you have an object P, and if the angles are small, then to an outside observer here in this environment where the index of refraction is n2 and it's smaller than n1, it looks like that this object is closer. In other words, it forms a virtual image that's kind of closer to the interface. That's just a direct consequence of how these rays bend. Okay, so here is a quick question. So pause the video, try to figure out the answer. All right, so we have a fish in an aquarium with flat sides, so it's looking out at a hungry cat. So to the fish, the distance to the cat appears to be what? So first, we already figured out, like, to the cat. So the cat, let's say, is outside, is in air, and the fish is in water. So for water, N1, the index of refraction is larger than N2. So to the cat, the fish looks closer, for sure, right? That's what we talked about. So now the question is, what does the fish see? So if the observer, namely the fish, is here, how would the fish see the cat? So we have to think about the rays that are emitted from the cat, right? So let's consider one of those rays going that way. Then what happens? As it enters the water, it should get closer to normal, right? So as an example, let's just consider one of those rays, right? That's a ray from the cat. This is the normal. It should get closer to the normal, so it bends this way. And if we continue, it looks like it's coming from somewhere behind the cat. So that's the correct answer. So the fish imagines that the cat is somewhere, farther away than its actual distance. Right. So those are the rays, right? This is the cat. These are lots of rays from the cat, and they all bend toward the normal, which is the horizontal line here. So if you trace them back, the virtual image of the cat is going to be a longer distance from the interface than where the cat is. Okay. So here's an example. Again, let's read through this and then pause the video, try to find the solution. So we have a fish and a sailor that look at each other through a 5 centimeter thick glass. And then there is an air bubble right in the center of the glass. Okay. So the sailor, of course, is inside the submarine, so there's air where the sailor is. The fish is inside water. There's glass between them. And there is an air bubble inside the glass. All right, so yeah, pause the video. And when you're ready, come back, we discuss the solution. All right, so this is a direct application of the formula we just discussed, right? So from the point of view of the sailor, let's say sailor is here. The air bubble, which is an object inside the glass, is going to appear closer to the sailor. So S is 2.5 centimeters, right? It's a glass of thickness half a centimeter. Sorry, it's let's see. Yeah, it's a 5 centimeter thick glass, and then half of it, if it's right in the middle, is going to be 2.5. So we just want to see where it is, and if we apply our formula, come back to the minus sign in a second. So for now, just ignore the minus sign. Let's say there's absolute value on S and S prime, right? So the absolute value of S prime is going to be N2 over N1. So that's for the fish, right? Which is 1.33 divided by 1.5. So it's gonna be like the fish is gonna see it closer. The sailor, the index of refraction of air. So 1.33 is the index of refraction of water. 1.5 is glass. Here we use the same formula when we're thinking about the sailor, but we have to use air instead of water. So this minus sign in the formula is quite useful. It basically, there's a convention that says real objects have a positive distance. So S is a positive number from the interface, and virtual images have a negative distance. So this basically implies that the image is on the same side as the object. It's virtual. It's not that the rays physically converge somewhere. You have to trace them back. So the correct formula, if you want the formula to give you whether the image is real or virtual, has a minus sign, and then S should be entered as a positive number because the object is real, and S prime, because if you put that minus sign in the formula, you get a negative number, which means it's it's a virtual image. Okay. Now, so this was a little bit of an introduction to what kind of going across interfaces can do to light, and we just talked about a flat interface between one medium and another. Now, an important application of this is having curved interfaces. So lenses are basically made from a piece of glass or something that has an index of refraction that's larger than 1, and they can either kind of be converging. So if you shine, let's say, parallel rays on it, they bend toward each other and they converge at one point. Or so that's a converging lens. Or they can be diverging like this. Okay, so in the same way that, we found in the limit of small angles, we found that just going across a single flat interface, we get a point image for a point object, so we get a sharp image. Lenses, in the limit that they're thin and the angles are small, one can show, and we'll discuss it to some extent later, they can basically converge all parallel rays at one point. So let's say ideal behavior of a lens. So let's say you have a converging lens here. So let's first discuss the ideal behavior of a lens. So when we were talking about refraction across a flat interface, we had some exact expression that was kind of complicated, but in the limit of small angles, we found this very simple expression which implied that, the image of a point object is a sharp point. Kind of, it becomes independent of the angle, right, where the image is formed. All these rays that are refracted, they seem to originate from one point. One can study lenses which are basically thought of as two spherical surfaces. So this can be, let's say, part of one sphere, and this can be part of another sphere. So if you have a thin lens, and in the limit of, again, when it's thin, these are very close to each other, and angles are small, a kind of ideal behavior emerges, similar to what we talked about for refraction across a flat interface. We'll talk quite a bit more about this, but before kind of trying to understand where this comes from, let's try to work with it a little bit. So it's the technique that we use to work with these ideal lenses is something called ray tracing. Okay, so let's say this is a converging lens. And in the ideal case, what it does is that all these horizontal rays, regardless of their distance from, let's say, this central line, in this ideal approximation, they all converge on one point. So that's an ideal behavior that emerges in a certain limit. Okay, and this point is known as the focal point. So then, if I draw this kind of like that, say this is my converging lens, this is the center line. So if you have a ray parallel to this symmetry axis, then it's going there. Where this distance is called f, it's also known as the focal length. Another important feature is that a ray that goes through the center of the lens just keeps going, so it doesn't get refracted. And the lenses kind of behave in a symmetric way. So if you have, for example, a ray going through, let's say, the focal point here, so you can just change the direction, and then it becomes parallel to the symmetry axis. And of course the behavior is symmetric from left and right. So if you have, again, something like this going this way through the focal point from this side, it becomes parallel. And yeah, and similarly the opposite kind of direction of this. And if it comes this way parallel, on this side it goes through the focal point. So this distance is always f on both sides. That's the ideal behavior of a converging lens. A diverging lens, something like that. So I draw it once like this, and then I draw it like that. What it does is, so diverging. If you have parallel rays, approaching it, they diverge, they move away from this line in such a way that if you trace them back, they appear to be coming from a point, a distance f behind the lens. Okay, so one way to think about it is that if you shine like a beam of parallel rays on a converging lens, they create a real image on this side. So these rays really physically converge on one point over here. And a beam of parallel rays incident on a diverging lens creates a virtual image behind the lens, a distance equal to the focal length of the lens. Okay, so this is a better picture for a converging lens. By the way, this line kind of perpendicular to the lens going through its center is also known as the optical axis. These are these parallel rays, so they get focused on the focal point. The diverging lens behaves like this. All right. Okay, so here's a quick question. Pause the video and try to decide which one's correct. All right, so yeah, so to start a fire, you need a high intensity. So physically, you need to have a point, right, where the light kind of gets focused and converges. So a converging lens does it. A diverging lens, no. I mean that focal point, there is no physical light there, right? It's a virtual image. So the rays just move away, and this point is not a physical point, right? You have to just imagine that these lines extend behind it. So yeah, the converging lens would do the trick. Okay. So these are the rules we kind of discussed, right? For ray tracing, basically these parallel rays parallel to the optical axis all go through the focal point. Similarly, from this side, if they go through the focal point, they become parallel to the optical axis. And then the rays going through the center don't refract, they just move straight. Okay. So now these rules are the basis of figuring out where the image of an object forms and how large it is. Is it inverted or not, etc. So that's ray tracing. Basically, by looking at a bunch of particular rays from different points of an object, one can construct the image. All right, so let's draw a better picture. So what we want to do is ray tracing for a converging lens. All right. So consider, let's say this is the optical axis. Here's our lens. Let's say these are the two focal points. And imagine I put an object somewhere over here. Okay. So we want to find the image of that object, and we're going to do this point by point. So we want to find the image of every point belonging to this object. So let me take this one point, let's say, at the top of the object, and imagine the object has a height L, right? That's its size. And it's a distance S from the lens. Again, the focal distance is F. So this is F, this is F. All right, so assuming that every point, again, gives a sharp point-like image, let me just draw two rays which I know how they behave. So one ray goes parallel to the axis, hits the lens, then it bends and goes through the focal point on the other side. I can similarly draw a ray that goes through the focal point on this side, and then on the other side it would move parallel to the axis. So it does that. Okay, so there's going to be this point over here where these two rays cross. And if, that point forms a sharp image, so if all the rays that are emitted from this point as they go through the lens end up at one point, it has to be this point because two of them cross at that point. Okay, so let's first try to figure out where that point is. Exactly, so it's going to be some horizontal distance from the lens and it's going to be some vertical distance from the optical axis. So let's call this S prime. That's the position of the image. And let's call this L prime. That's kind of the size of the image, right? So if, all the points now from the top to the bottom end up on that line, the image gets formed over here and it's going to be some inverted image. All right, so how can we find these distances? Well, it's a relatively simple exercise, right? So we know the geometric construction that led to this point. So if we stare at the figure, we can identify a bunch of similar triangles. So you see these two triangles, one here. These are two right triangles that have the same angles. Similarly, these, let me draw that in red. It's more visible. Sorry, I don't want to do that. I want to draw this and that. Again, these are two right triangles that have the same angles. So they're similar. Okay. Now, so in these triangles, let's identify the various lengths. So let me draw the blue ones again over here. So this length from here to here is L. This is L prime, right? See, L prime is from here to here, but these two are parallel, right? So that's this is a line parallel to the optical axis. So that's just a rectangle. And then this side of the blue triangle is going to be L prime again. This from here to here I have F. And from here to here I have S minus F, right? This whole length from here, from the object to the lens is S. And then from the lens to the focal point is F. So here the distance that's left over is S minus F. Okay. Now let me draw the other two similar triangles. Again, here we have L prime. Now this side is L. Again, this line is parallel to the optical axis. This distance from here to here is F. And this distance from here to here is going to be S prime minus F, right? So from here to here I have S prime, and from here to here I have F. So this is S prime minus F. All right, so now if I want to write equations relating these lengths, I can write these are similar triangles, so L prime over L is going to be F over S minus F. On this side, I find L prime over L is S prime minus F over F. And then these two expressions must be equal. They're both the ratio of L prime to L. And then I get an equation that relates S prime, and F. So for example, if I have a lens that has a focal length F, and I put an object, a distance S from this lens, I can solve for S prime and figure out where the image would form. So let's write that equation. So we have F over S minus F is S prime minus F over F. We can simplify this equation. There's a much nicer form that's very easy to remember, which is just equivalent to this up to some algebra. So let's do that. So if I take this and multiply both sides by F, so I cancel out this F in the denominator, and multiply by S minus F, so to cancel this out, I find F squared, so get rid of the denominator, multiply by F, is going to be S prime minus F times S minus F. Again, get rid of the F and multiply by this. Okay, so what is this? If I expand that out, it's going to be S prime times S minus S prime times F minus F times S plus F squared. Okay. So then F squared cancels. Let me take these to the other side, factor out the F. So I find F times S plus S prime is S times S prime. That means that 1 over F, let's say we divide it by F and divide it by S times S prime, becomes S plus S prime over S times S prime. And this is S over S times S prime, which is 1 over S prime, plus S prime over S times S prime, which is 1 over S. So that's 1 over S plus 1 over S prime. Okay, so that's known as the thin lens equation. 1 over F, or let's write it the other way. 1 over S plus 1 over S prime is 1 over F. So that's an equation that relates the distance between the lens and the object, the distance between the lens and the image, and the focal length of the lens. All right. So again, that's a better picture. Now it turns out that in the limit of a thin lens with small angles, so all these angles are small, kind of almost parallel to the optical axis, then all the rays coming from this point will go through that point. So let's check it for one particular ray. So we had this rule about the ray going through the center not bending, just going straight. So let's check that. So going back to this figure, right, let's consider this ray here. So what is the condition that this goes straight. So if that goes straight, see on this side, right, we're gonna have length L and S, the distance between the object and the lens, and on that side you're gonna have S prime here and L prime. So the condition in order for this ray that goes through the center not bend is L prime over L is S prime over S. Okay, can we check that it works? Well, let's take a look at L prime over L. So I can write, for example, from this equation, let's use that, is L prime over L is S prime minus F over F. Which is S prime over F minus 1. And I know 1 over F is 1 over S plus 1 over S prime. So L prime over L becomes S prime times 1 over S plus 1 over S prime minus 1. And yeah, so then this is S prime over S plus S prime over S prime, which is 1 minus 1. So that goes to 0. So yeah, L prime over L is S prime over S. It does work for the central ray. And you know, an alternative way would have been to just use the central ray and one of these rays, either this or that, to find the position of the image. So the lesson is, you know, we get this image that's inverted, and we know where it appears. We also know how large it is, right? As long as we find, let's say, S prime, we know that its size, L prime, is just S prime over S times L. All right, so that's a good place to stop. In the next lecture, we practice a lot kind of using this equation. We'll solve a bunch of problems. And we extend our results to diverging lenses as well. So here we treated F, S, and S prime as just positive numbers. And there are some rules that we'll discuss. We can assign some negative signs to these, so our equation works for both converging lenses and diverging lenses. All right. See you in the next lecture.